In the previous part of this lecture, we saw that when we talk about multi-component distillation, it requires multiple columns in a sequence, and there are many alternative sequences as well. And they don't all perform equally well, so it means that it could be a huge amount of work to evaluate them all. And then we saw some practical constraints that can help us reduce the number of these sequences that we need to evaluate. In addition to practical constraints, we can also use other approaches, like that's what we call heuristics. And these heuristics are usually common sense criteria. They are based on observations made in many problems and attempts to generalize the observations. So these heuristics are actually industry guidelines on how the columns in a sequence should be arranged, and by following these heuristics, we can reduce the number of sequences that we need to evaluate in terms of their performance. And these heuristics or industrial gradations, they are normally restricted to simple columns with no heat integration. But very often these heuristics lead to conflicting solutions. Okay, so we can also use quantitative methods which involve mathematical modeling of different separation configurations to minimize one or more output variables. So in the simple sense, we could either use heuristics that are mostly based on common sense, or we can use quantitative methods that are based on objective methods that are usually linked to maximization or minimization of specific variables or multiple variables in order to come up with the best distillation column sequence. So let's have a look at these heuristics. So there are four heuristics which were gathered from industrial experience. So let's start with heuristic number one, which suggests that separations where the relative volatility of the key component is close to 1, or where you have an azeotropic behavior, should be performed in the absence of non-key components. So what it means is that the most difficult separation should be the last in the sequence. Note that the reverse logic is not true. Nobody says that do the easy separation first. And if you think about it, it makes sense because we are trying to isolate the most difficult separation between two binary components, and because it is the most difficult separation, so we don't want to perform it first, because otherwise we need to have a very large column. So we make sure that first we remove the easy separation, we perform the easy separation, and once that is done, then we can perform the difficult separation, or even see the need to perform that difficult separation or not. The second sequence states that the sequences which remove the lightest components alone, one by one in the column overhead, should be favored. And that means that if you have four components, the first column would remove the lightest one, the second column would remove the second lightest, and the third column would separate between the third lightest and the heaviest components. And this is what we call a direct sequence, as we discussed in previous part. And opposite to that, we have an indirect sequence, that is where the heaviest component is removed successively in each column. Okay. The third heuristic is that if you have a component which comprises a large fraction of the feed, you should try to remove it first, or at least early in the sequence. And the logic here is that if you have a large flow rate and you can remove it from the system early on, then you will have lower flow rate going through the sequence, as such reducing the size of the equipment and the duties of the reboiler and the condenser. The fourth heuristic is that if we are looking to do a separation, we would try to find a balance between the distillate molar flow rate and the bottom molar flow rate. That is an equimolar split between the top and the bottom product. And this doesn't mean exactly a 50-50 split. It just means that something close to that, okay? So that you try to balance the load between a condenser and the reboiler. Now, how close is close enough? Well, that is the problem with these heuristics, because they are not exact, and that's why sometimes they also lead to some conflicting sequence or conflicting results in terms of which sequences are the best. So these heuristics should be used as a guideline just to reduce the number of your sequence options. There are some questions in the problem set, so please try to engage with the problem set and try to use these heuristics to find the best possible sequence. We will also practice some work examples in the synchronous session around the concept of heuristics and quantitative method of evaluating a sequence. So now let's have a look at a quantitative method that use more of a rigorous analysis to help us evaluate the performance of a sequence of a distillation column. And it look at certain variable and try to minimize or maximize the output of that specific variable. So what kind of variable can help us with this problem? And the variable is vapor flow upward the column. So why vapor flow up? This is so important because vapor flow up the column can be regarded as a cost-related entity affecting both the capex and the opex of the column. So first of all, it affects the column diameter because, of course, a distillation column that needs to deal with higher volumetric flow rate of vapor and consequently also liquid will require a large column diameter, and diameter is directly related with the capex of your distillation column. At the same time, if your vapor flow rate is quite large, obviously that is going to affect the condenser duty and the reboiler duty as well, because the condenser has to condense a large amount of vapor, while the reboiler will have to reboil the higher amount of liquid as well. So therefore, the vapor flow rate of the column is a very good indicator of both the capital and operating cost for individual columns. So consequently, sequences with lower total vapor load should be preferred to those with a high total vapor load. So before I go into detail of this quantitative method to evaluate sequence of distillation columns, I need to introduce some basic fundamental equations that we use for design of multi-component distillation columns. You will cover these equations in much more detail in the unit of multi-component engineering separations. Here I'm just going to introduce you the equations, so please bear with me. The background of these equations will be covered in multi-component engineering separations. The reason I have to introduce these equations here because later on we want to use these equations in developing the method to evaluate the performance of a distillation sequence. If you remember from your binary component distillation, there are two limiting conditions. The first limiting condition is the total reflux, in which case there will be no feed, no product, and this limiting condition normally gives us the information about the minimum number of equilibrium stages and also how the components are distributed between the distillate and the bottom. And then we have the second limiting case, which relies on the minimum reflux ratio. And in this case, of course, we are going to get a pinch, if you remember. And this method normally provides us the information in terms of the minimum reflux ratio and again, the distribution of the components in the recycle stream. So the first equation is what we call Penske's equation, and it is an equation that gives us the estimation of minimum number of stages, and the assumptions that we use for this equation are total reflux. It means you don't have any product. You have constant relative volatility, and that is a very common assumption that we take also for binary component distillation as well. And third one is that there is no pressure drop. So now let's try to write this equation, and let's say that you have a distillation column and you have two components here like I and J, and that would be the binding component distillation. But for the case of multi-component distillation, because you have more than two components, so you will have, let's say, I, J, and K or L. And so what you do normally that you try to identify a light key component and a heavy key component, as we discussed in the previous part of this lecture. And this light key component and the heavy key component, you try to focus your separation for these two components, and then you can write your equation in the same way that would be an analogous to a binary component distillation. Okay, so if you focus on I as a light key component and J as a heavy key component, and all the other components that what we call non-key components, they will be just distributed between distillate and the bottom product based on their relative volatilities. Okay. So in this case, we have minimum number of stages, and that would be equal to log of XLD, that is the mole fraction of light key component in distillate relative to the mole fraction of heavy key component into the distillate, and then you have similarly mole fraction ratio of heavy to light key component in the bottom product, and then you have the relative volatility of light to heavy key component. So this is, again, as I said, I'm just introducing this equation. You will cover this equation in much more detail, and the derivation of this equation, how you get this equation by doing material balance, and so that will be covered in multi-component engineering separation unit. Now let's have a look at our second set of equations. So here we have the equation that we call Underwood equations. And in Underwood equation, instead of calculating the number of units, we actually focus on the calculation of minimum reflux ratio. Okay, and again, we have the assumption of constant relative volatility, just as the case of Fensky equation, and we also have that there is no pressure drop in the column. Again, I'm not going to go into the derivation of these equations. You can find the derivation of these equations in any book on separation processes, and also the derivation of these equations would be covered in multi-component engineering separation unit. So again, please bear with me. I'm just going to introduce these equations. So here what you have is that you have the first equation where you have the sum of this term here, and this term we can write it for a component I going from 1 to the number of components in your system. Okay, and alpha ij is the relative volatility of a component. Then you have z, that is the mole fraction of that component in the feed, and then you have 1 minus q, and q is the thermal condition of your feed. Okay, as you remember from your binary component distillation. Okay, and now this first equation is characterized by this variable here theta, that is the root of the equation. So if we have, let's say, nc components, we can have nc minus 1 number of roots lying between the relative volatilities of all the components. But of course, for our calculations, we should focus mainly on theta values which lie between the two relative volatility of light key and the heavy key component. So after solving this first equation, we use the value of theta that I said should be between the relative volatilities of light key and heavy key components. We determine this value here, and then we input this value in the second equation, and from the second equation we can get the minimum reflux ratio. Okay, and again, as you can see that the two equations look very similar. You have same relative volatilities. You have the root of the equation that we calculated from first equation. The small difference is that here you have the feed fraction of the mole fraction of the feed of component I, while here you have the mole fraction of component I in the distillate. Okay, we are not looking at the whole feed now. And again, you will discuss these two equations in much more detail in multi-component engineering separation unit. So having determined the minimum number of stages from Fensky's equation and then the minimum reflux ratio by using Underwood equation, we can move forward and calculate our actual number of stages. And for that, we can use an empirical correlation of Gilliland. Okay, so this is how it looks like, and it is actually developed by looking at, for example, experimental data. Okay, so here you have on y-axis you have n minus n minimum. Okay, and n minimum is the minimum number of stages, and n is actually the actual number of stages, and then you have x, that you have actual reflux ratio minus the minimum reflux ratio. So normally we can assume a suitable value of actual reflux ratio. So let's say 1.1 time of minimum reflux ratio, as we discussed in the previous part as well. And then by defining R minimum or R, we can actually determine X, and then based on the value of X, we can determine the value of Y based on the value of N minimum, because in this equation then we know already N minimum, so the only variable that we have is actually N here. So by using Underwood and Fensky equation and then using the Gilliland correlation, we can actually determine the actual number of stages of a distillation column. Again, you will discuss these equations in multi-component engineering separation unit.